for the morning session today. It's a bit after the morning. And it's a pleasure to have Gabriel Kerr from Kansas.
Kansas State.
Kansas State.
I'm not offended, but
talking about neurosymmetry for elementary birational cobordisms.
okay. Well, thanks very much to the organizers for inviting me. It's a pleasure to be here. So today I want to talk about homological neurosymmetry for elementary birational cobordisms, and I'll try to explain some of the words in that title. All right, so here's my outline. I'm going to start by just giving a general setup of the kind of question I'm going to answer, and I won't really give a proof of this, but maybe online I'll give some notes that are a little more extended with proof, or at least a sketch of a proof. So this will be fairly vague, and in the second two sections I'll give a more precise notion of what I mean in this motivational part. All right, so let me start there. So what kind of version of homological neurosymmetry am I thinking about? I'm going to be thinking about the case where I have a Deligne-Mumford stack, X, and then I have some mirror potential, which is going to be some holomorphic function on a mirror manifold to C. And the particular version of homological neurosymmetry I'm looking at is an equivalence between two triangulated categories, or derived categories. One is the derived category of coherent sheaves on X, which is on the left-hand side, and the other is known as the Fukaya Seidel category of this function W. So we can think of, if we're thinking of the last talk, this function W will be some Lefschetz fibration on the mirror manifold. So under these circumstances, with some conditions, we can define this Fukaya Seidel case.
So the mirror manifold is manifold. I mean, even though X is a stock, the mirror manifold is an always manifold.
Yeah, in this case. So as I said, I'll be very vague here, but I'll be more precise. All right. So, of course, both sides of this equivalence, or this conjectural equivalence, are very complicated on their face. And so I'm going to ask some very naive questions about both of them. And the first question is, are there natural decompositions for either side of this equivalence? And then the second question is, if I had some natural decomposition of the category on the left and some natural decomposition of the category on the right, is there a way of that homological neurosymmetry will send one to the other? So will this equivalence respect these decompositions in some nice way? Okay, so let me take the first question first. Well, there are a lot of natural decompositions for a derived category of coherent sheaves on let's say a variety or a stack. But the one I want to look at comes from maybe birational geometry, and maybe is pioneered by Pondo and Orlov, but there's a lot of more recent works considering this from variation of GIT rather than a minimal model sequence. But anyway, so suppose we have some minimal model sequence on X given by a set of birational maps, and then maybe FR is some kind of Mori fibration or something slightly more general. Then there are some results that say that we can decompose our category of coherent sheaves into some semi-orthogonal decomposition, where each of these little categories comes from a particular birational map, or variation of GIT, and then at the end you're left with sort of the derived category of some minimal model. And so if we think of this rather than thinking of this as a minimal model sequence but a variation of GIT, we can sometimes end up with a vacuum at the end, and then this category is 0, and we've just decomposed our derived category into a bunch of subcategories. The structure of these subcategories is really understood from this variation of GITs. These are called wall contribution categories. In practice, the way you get something like this, or at least the way I would get something like this, is we start in this Picard, you start in your Neff cone, and you take some straight line to the boundary of your effective cone, and you're crossing sort of walls in some Mori fan, and each time you cross a wall, you get one of these variations. So this is a nice answer, and there's a lot of literature to describe this answer on the B model side. So what about the A model side? Well, this is a little more delicate. We need to take a few steps to describe the answer here. So the first step is I want to replace my Lefschetz fibration, W, which is some holomorphic function, just conceptually with a different function, which is, I wrote it as lowercase w. And instead of thinking this is a holomorphic function from some variety to, say, C, I'll think of this as a one-parameter family of hypersurfaces in my mirror manifold. And so then if I'm in a good situation, I have some moduli stack of such hypersurfaces, and I can just think of this function as being pulled back from some representing function from C to my moduli stack of hypersurfaces. So that's my first step. It's just reimagining my potential as a function from C to a moduli stack. And the next step, I just compactify all things that I can. So I'll compactify the range of my potential to P1. I have some nice compactifications in mind of my moduli stack of hypersurfaces and their degenerations. And then that leads me to some compactification of the mirror manifold. But here, really, I haven't done anything yet. And so the thing to do at this stage is to then deform my compactification over some disk, say. So here I put some parameter on my potential, say t, so that at 1 it's equal to my nice, the potential that represented the original potential. And then I take t going to 0, and I see what happens. All right, so here's kind of a picture of what would happen. So this is the image at t equaling 1 inside of my moduli stack. And I imagine, well, this is some moduli stack of hypersurfaces, and so inside of that moduli stack of hypersurfaces, I have all the singular hypersurfaces. Right? And so I indicate the intersection of the image of W1 with those with that discriminant variety in sort of red points. And then I start deforming, and I go to some limit, some maximal limit, and I bubbled off a bunch of P1s, and this is the advantage of doing a nice compactification, is I get some stable limit. And if I do everything nicely, I can hope that I've isolated a bunch of critical values of my potential on each of these components in this limiting map. Okay.
The choice you're making here about how to degenerate this corresponds to the choice of which direction you go in the comic book.
Okay, that's exactly right. So yeah, there's a lot of possible degenerations, just like there are a lot of possible minimal models, minimal model runs. But there's some correspondence between these. So, in fact, so one thing to say for those that haven't looked at Fukaya Seidel categories, at least in this context, is that these red points are really important for Fukaya Seidel categories. The way you define them is well, one way of defining them is you can take a bunch of paths to these points. These paths will give you objects in a particular category, and then those objects generate this Fukaya Seidel category. So what happens through this procedure is you're organizing these critical values into groups. And that organization then can be unraveled in such a way as to give you Fukaya Seidels for each of these pieces and a semi-orthogonal decomposition for the global category. And so that's the last step, is that over each of these components in the limit, you want to pull back this limiting representing map to give you sort of individual potentials, and then consider Fukaya Seidel categories of these pieces, and in this case we'll get a semi-orthogonal decomposition of the initial Fukaya Seidel in terms of these pieces. So this is my natural way of decomposing Fukaya side. Okay. Yes. Huh? What was U? U is this universal hypersurface over the moduli state. All right. So now the second question, we have a decomposition on the B model side, and we have a decomposition on the A model side. And is it the case that these the homological mirror symmetry will send one such decomposition to the other? So in the toric setting, which is really setting I'll focus on today, along with Colin Deemer and Lumil Sarkov, we gave an explicit prescription for taking one of these, well, straight line minimal model runs, or variation of GIT, a sequence, to a particular degeneration, very prescriptive degeneration of mirror potentials. In fact, where you can really just write down coefficients of the potential to tell you which direction you want to go.
Sorry, outside of toric setting, is it almost possible to have a BGID sequence which terminates in 0?
No. No. But, well, hopefully we'll learn something that we could apply outside of this. And furthermore, we have a theorem that will say that, or we have a theorem that says that the rank of the K theories, or the growth indeed groups of these semi-orthogonal components, that they're equal on the A model side and the B model side. So the number of critical points was equal to, in this limit on the A model side, was equal to some exceptional collection given by Kawamoto on the B model side. And so this is, at least we took this as very strong evidence that we could get corresponding decompositions, and that at least they look like they might be equivalent. All right, but it left open, of course, the actual equivalence of categories, which needed to be proven, and still needs to be proven in general. Okay, so that's my motivation, is to prove that statement, that at least there exists an equivalence of categories between these pieces, at least in some understandable cases, some elementary cases. All right. So now that was very vague. I understand that, and now I want to be more precise about these variations of GIT, and in particular these pieces that we're getting. Okay. So what is an elementary birational cobordism? So I'm taking a little bit of liberty with these. You can do something slightly more general, and I think call it an elementary birational cobordism, but mine will be special cases, let's say. So I'm going to start with just some lattice element with coordinates a0, 3d, and I'm going to assume that all of these are non-zero, and really that's it. And then I'm going to describe a variation of GIT given this element A, or this lattice element. And basically this is just a character for a C-star action on affine space. But of course, when you have an action of C-star, well, of a group on affine space, there are a lot of different ways of quotienting, depending on what your polarization is. So if you want to do GIT, you need to choose polarization, or a positive or a negative line bundle, given by a positive or negative character on C-star. And in these two different cases, you'll get different unstable loci, which are both coordinate planes. The B minus is going to correspond to just setting all of the coordinates equal to 0, where AI is less than 0. And similarly, the B plus is, we take ZI equals 0 if AI is positive. So if you excise these unstable loci, then you can form the nice GIT quotient just by quotienting by the action. And this is the variation of GIT that I want to consider. These are my elementary birational cobordisms. So maybe it's worth doing some examples in this case right away. So one example, you could take all of these AIs to be positive. Yeah. If you take all of the AIs to be positive, well, then B minus is sort of a vacuous condition. So B minus just contains everything. This is all of affine space. So if you remove B minus, right, to get X minus, you get the empty set. On the other hand, B plus is just the point 0. You remove 0 and you take your quotient, and you'll get weighted projective space with A0 through AD as your weights. So this describes going from weighted projective space to the vacuum. If you let just one of these be negative and all the others be positive, then this will describe a weighted blow-up of a point. If you take 2 to be negative and the rest to be positive, then you get a notion of a flip. Well, let's say that D is greater than 2. Then you get a flip. And so yeah, so these describe a lot of the elementary birational transformations that you see as your first examples of birational transformations. All right, so now I'm going to add one more number, which is just the sum of all the AIs, and I'll take its negative, and I'm just going to add that as a final coordinate, bringing up my rank by 1. And I do that for reasons, well, we'll see later why we may want to do this. But once I do this, then I have this nice, well, even before I did that, I have a nice theorem by, I think in this context, originally by Kawamata, but there's a much more general version of this by Ballard, Favero, and Zarkov, and by Halpern Leisner, which describes the derived category coherent sheaves on the plus quotient in terms of that of the minus quotient and an additional semi-orthogonal component, which I'm writing here as TV sub A. Furthermore, because really I made that choice that all of the AIs are non-zero, in this particular case, this category, this component category has a complete exceptional collection, which is certainly not true in more general cases. Furthermore, if I want to understand, say, this collection, there's a nice way of understanding it by just taking this category and embedding it into the equivariant sheaves on just affine space, C to the D plus 1. And here, then, these objects, E0 through E, well, through this last exceptional object, are just the equivariant structure sheaves of B minus, with a weight shifting by I. So the I exceptional object has its weight shifted by I.
What's X?
X is affine space. Just C D plus 1. So this is just C star is just I keep X around because maybe X is really a local model, right? We can think of this as acting on some variety. We have some local model near a point where we're doing this transformation. But yeah, let's just take X to be. All right, so now the point is that not all complete exceptional collections are alike, and one thing you might want to know is how do we describe this category, which is this semi-orthogonal piece. And so an equivalent question is, what is the endomorphism, or the DG algebra of the endomorphism algebra of the direct sum of these exceptional objects? So if you can describe that, then you will have an understanding, or at least a representation, of this semi-orthogonal component. And so that's what we want to compute, but this is actually kind of more or less an elementary exercise in homological algebra. All you have to do first is you take your equivariant sheaf on affine space and recognize that if I'm going to do some weight shifting, that the endomorphism algebra, well, that Hom from F shifted by I, F shifted by J, is the same thing as just looking at the endomorphism algebra in the ordinary non-equivariant category, but then looking at the graded piece that is of degree J minus I. So this means that if I want to compute this, really I just need to look at the endomorphism algebra of OB minus, where F is OB minus, and understanding that endomorphism algebra will give me full structure. But of course, this is an elementary computation where you see that the endomorphism algebra in this setting is actually formal, it's quasi-isomorphic to its ext, just using causal resolution, which in this case is just the exterior algebra of the conormal bundle. But this exterior algebra of the conormal bundle is just is a supersymmetric algebra of a vector space. And let me just say what this vector space is. So this vector space V0, well, you just take, again, I mean, you rely on this element A, you take the monomial, this should be taken as a spanning set here. So just take the monomials where AI is positive, and take the one forms DZI where AI is negative. And so then this makes a graded vector space, and to distinguish degree, the homological degree from the weight of the action, I'll write weight instead of degree. Of course, the weight of ZI is just coming from the character AI, and the weight of TZI requires a negative. But what that says is, of course, this is just going to be some positive weighted space, vector space, and we take the supersymmetric algebra where the supersymmetry is coming from the degree rather than the weight. And so then, if I call RA this supersymmetric algebra, which this is just a polynomial algebra in the super sense, I can isolate the degree K part, and then this gives me a nice representation of this the category as modules over a particular endomorphism. So let me write out a few examples just to get our heads around this. So A is 1, 1, 2, or negative 2. Then again, we have three variables, Z0, Z1, DZ2. This is again a case where all of these A's were positive, and then I added that A D plus 1 at the end, which of course will have to be negative. And well, the sum of these guys is of all the AIs except the last one is, well, this, the absolute value of this. So I have two objects. I have a Z1 and a Z0. And of course, as everyone knows, or many people know, this is just a Kronecker quiver, which gives us a valence and exceptional collection for P1. You can do this for weighted projective line or weighted projective space. Here you have 5 objects. You have to take the sum of these guys, and then the weights of the monomials are slightly different. So
the parentheses with the number, what does it do?
With this A? So this.
No, I mean the RA is okay, but then RA is parenthesis 3. What is the 3?
RA3. This one?
Yeah, what is the 3?
Yeah. So this is RA is this, but this has actually two. It's bi-graded. The DZ has a degree 1.
That's right.
It's a homological degree, and then the Z0, Z1, and well, the Z0 and Z1 have weights 2 and 3, and the DZ has a weight 5 because we have a negative there.
That's right.
So this is a bi-graded space, and so the module is just shifting the weight, not the degree.
Okay.
Just the weight. So that's what this 3 represents there. And it should shift it negatively as per the convention. All right. And then if you want something where you don't have the vacuum on the other side, you can consider the tautological bundle over weighted projective plane. Here you'll see some of the DZs in there. You've got some nice quiver. You have the super, so there are some, the previous two don't have any real relations, but here you have some quadratic relations. Again, these just come from the polynomial algebra. So Z0 times Z1 is Z1 times Z0, and so on and so forth. Good. So this gives us a very clear representation of this category, which is the semi-orthogonal piece, and it's just, again, the modules over this algebra. This over algebra with relations. Okay. So now I'm just going to briefly discuss the A model.
Now let me get this right. Every example was non-compact.
Every example was I don't know what it means.
Well, you have these local models, so you always have
Yes.
this It says surgeries.
Yes, yes. The sheaves are all supported on a compact subspace.
Okay.
That will be true, but then certainly the GIT transition is, I mean, we're on affine space, so that's not compact. And so, but, so if you look at something like this, you have this exceptional divisor, and the sheaves will be supported on that exceptional divisor. So that's going to be compact. So what are these component categories on the A model side? Well, so for this, I want to first look at the most elementary possible, well, maybe not the most, but one of the most elementary symplectic luscious vibrations I can. The only difference will be that it doesn't go to P1 or C, but it goes to C star. And it has just has a single unique critical point P with critical value Q, and this is a Morse, by the definition of symplectic luscious vibration, it's a nice Morse critical point. And I want to take something like this, and I want to build a Fukaya Seidel category out of just something like this. And the way I do it is I choose some other base point, let's say close to 0, and I take a path from my critical point, or critical value, excuse me, to this base point. And then this gives a vanishing, what's known as a vanishing thimble. If I just take symplectic parallel transport, and I imagine flowing into that, all things that flow into this critical point, what it will do is it'll trace out some ball, and that ball is a Lagrangian ball, of course with a boundary of Lagrangian sphere right over this fiber here. Now, if I'm in the exact setting, which I'm going to assume I am, what I'll have is, over the fiber, I'll have some exact symplectic manifold, and I'll have a nice exact sphere, which is this vanishing cycle, and then I can try to build a Fukaya category just by taking the category generated by this one Lagrangian inside of my fiber. But of course, that's not going to give me a very interesting category, and so if I want more objects, and all I have is this atomic luscious vibration, I just apply monodromy, and I'll get a new path with a new vanishing cycle, and I'll do it again, and I can get many, many objects in my fiber, as many as I like, really. And so in this situation where I just have this atomic luscious vibration, I can define a category that I'll call the n-unfolded category, which is some directed A-infinity subcategory of this Fukaya category, just made up of these Lagrangians. So again, this is the Fukaya category of the fiber of my chosen base point. And then the Fukaya Seidel category is just the category of twisted complexes of this directed A-infinity subcategory. So what do I mean by directed? What I mean is I just enforce a rule, and the rule says that if I'm going forward, I'll keep all of my morphisms. If I go backwards, I have no morphisms, and otherwise I just keep the identity from an object to itself. And this gives me a nice A-infinity algebra, which is the endomorphism algebra of the sum of these objects, and I can talk about twisted complexes over that A-infinity algebra. Yeah. That's
How
okay.
do you get this money? Which choices did you make? Which choices did you make to get those vanishing cycles? On the previous slide, you very quickly said that you choose 8 different paths, get different monodromies, but now we ended up with a finite set of vanishing cycles.
I go from, so each time I do apply monodromy, I introduce, so in other words, I go around 1, 1.
Yeah.
I add another one. So I'll go, the only thing I choose here is n. That
And what's
number.
n?
N is it's a choice.
Randomly choose.
It's a positive
integer.
A positive integer. Yeah. At this stage, that's all it is. So I call this the n.
So for any n, you can do this construct.
For any positive. So another way of doing this, if you don't like this prescription at all, which I can understand, is you take this, say the universal cover, take the log of this map, pull back, and now you get some very big symplectic manifold up here, and you can just isolate a little strip, and now you have over that strip a nice symplectic manifold with a finite number of more singularities, and you can take your usual Fukaya Seidel over that, and then a theorem of Seidel says that these two categories will be equivalent. You have to interpret a theorem of Seidel, but these two will be equivalent. All right. So I have 1 minute. Good. So let me just describe this particular case. So what is this? So I described this element A, and I said that this gave us an elementary birational cobordism. What is the mirror of that? Well, for that, you take a d-dimensional pair of pants, which is just a hypersurface setting all the sum of all of the coordinates equal to 0 in PD plus 1, and taking off the coordinate hyperplanes. Then you can define with this element A, where again we added that last element A d plus 1, you can define a pencil on your projective space, and it's given by just taking the monomial corresponding to the positive coordinates and the monomial corresponding to the negative coordinates, of course adding a negative so we have a positive, and then because of this homogeneity or balancing condition, we have an actual pencil given by psi A. And I can restrict that pencil to my d-dimensional pair of pants, and this is this mirror superpotential to this elementary birational cobordism, conjecturally. Well, so we showed in, I would say GKZ probably showed this without saying it this way, and then we just made the observation that this is then an atomic Lefschetz fibration, so it has one Morse critical point and one Morse critical value. And this potential really appears as an equivariant quotient of the homological mirror potential to VGIT as predicted by, say, Giventhal and Horiabov. And so then this is the theorem that I wanted to get to, which just says that if I take any n less than the sum of the positive coordinates and greater than or equal to 1, then there's this strict fully faithful functor relating this n unfolded category to the category modules, equivariant modules, over this algebra RA that we saw before. And it takes the kth Lagrangian, or at least a particular version of the kth Lagrangian, to this weighted module. Should do that there. So as a corollary, this is the last slide. So as a corollary, we get this equivalence in this case between these semi-orthogonal component categories. So we have homological mirror symmetry, at least in pieces, for these guys. And then as a special corollary of this corollary squared, we have the folklore result that if we just look at the case where all of the AIs are positive, except of course this d plus 1 that we added, then we get homological mirror symmetry for just weighted projective space, which was proved in the plane case by Baruch, Tsarkov, and Orlov, and in the unweighted case by Ueda and Fukaya, I think, and others. But I think this is the first time this level of generality is
I'm lost with the HB exponent.
Horikov.
Okay.
So the usual, so this is, the kind of notation to this particular talk, but these, in fact, this is exactly the Horikov potential. This is shown. So there are some preprints online under that prove this, but yeah, I'll stop there. Okay, thank you for your attention.
Any questions?
Yes. Do you have any ideas what will happen in the non-Fano case?
In the non-Fano case, I mean, so the hope is that if you have, let's say you have some so non-Fano, we've actually dealt with some non-Fano cases, even in the toric setting, and we're able to still run this kind of a program. And so I don't think, although you have to be a little more delicate, so the idea is you have some bigger Fano stack that you can get to the non-Fano case through partially going through a minimal model program. You get to something non-Fano, and then you do run this program from that point on. And that works just fine.
So you can actually take the minimal model program so that it becomes more Fano, right? And you run it back in that way? I mean, do you know what I'm saying?
I don't know if I completely...
So you can run the minimal model program against the
No, I think this is what I'm.
What you're saying.
What I'm saying, yeah. So yeah, I think in the non-final case, you can do it, and we can. The hope would be that in other cases, if you had a potential and you had a minimal model program, even if it was non-poric or more general situation, that these components will appear, and then you can reduce to some minimal model question for homological reasons.
And then you would have the same thing as you expect. That it would be the core buffer thing. That it would be a broad change of coordinates. Maybe.
Yeah, this horrible. Yeah, that's right. Okay.
Are there any general conditions to know whether a collection of Lagrangians is a complete exceptional collection, or it's such like crazy?
So if I look at a Fukaya Seidel category with Lefschetz fibration, then this is a theorem that this will give us a complete exceptional collection. It's almost a part of the one definition of such a category, is that the vanishing cycles coming from thimbles of a distinguished collection of paths generates the Fukaya Seidel category in that case. Oftentimes mirrors don't fit this nice norm, and so then you have to really ask yourself what kind of category this is, and many people are asking and answering that question in different ways.
Any other questions? Well, thank you very much. And now there is the launch at the Agave